here, Grassmann is a name. So just like you heard Riemannian or Eulerian or something like that, this is Grassmannian. And online, you guys can see this? Yes, good, thank you. So a K-plane in a vector space over field F is, anyone want to guess? Anyone want to guess? What do you think it is? It's just a subspace of dimension K. This is not supposed to be shocking. This is just supposed to give us a word for something that we already know. So the Grassmannian is GK of W, which is going to be the set of K-planes in W. Here W is a vector space over F. W could be infinite dimensional, but most of the time, and that comes up in math all the time, but you have to sort of go pretty abstract before you start dealing with the Grassmannian of all K-planes in an infinite dimensional space. So you should, for the moment, think of, you know, for the entirety of this course, think of W as being finite dimensional. Sorry, for the entirety of the Grassmannian part of this course. For many parts of this course, you do not want to assume that W is infinite, is finite dimensional. So this is a set, right? This is just a set of K-planes inside of a vector space. And the question is, what does this look like? Right? What does it feel like? What does it mean for one K-plane? So let's suppose that W was the real numbers. And then I could ask the question, what does it mean for this K-plane to be close to that K-plane? But certainly you have some notion, right, that if I take a plane in R3 and I just move it a little bit, that this one's close to that one, right? But, so that means that the set of K-planes, let's say the set of planes in R3, it's got some structure that's allowing you to say that this one's close to that one. That's kind of saying that the Grassmannian is in a metric space. What kind of metric space is the Grassmannian? How do you make sense of the fact that K-planes are close together, right? How would you, for instance, find the best K-plane for a given situation? And this is something that you've done before. So this is what I'll write down. So for instance, find the quote-unquote best K-plane for a given situation. Yeah, so what this, so for a given, let's say, purpose, problem. So what that would correspond to, this would correspond to some sort of optimization. It would be an optimization on whatever this set is, GK of, let's say, F to the N. Right? You would ask the question, so suppose I have some way of saying that a subspace is good. I want to find a best subspace that satisfies my criterion of being good. So what is the best one? So for example, you've seen this before. Remember least squares? What is least squares? Least squares is finding a line that is best for a certain purpose. And that purpose is that so this is called projective space of R to the N, which by definition is the Grassmannian of lines in R to the N. So this is the definition of projective space. This is projective space. Underline that. Right, so this P stands for projective. So this is the projective space of lines in R to the N, which is the same as the Grassmannian of one-dimensional subspaces of R to the N. So on that projective space, you want to do that for a cost function. So what's the cost function that we're using here? You're trying to say what is a best subspace here? What is a best line? Right? So we're looking over lines. So we're going to say that F of L for line is going to be the sum from I equals 1 to R of the distance from a point xi to L, and we want to square that. All right, so what this says is if you give me as input a line in Rn, and you give me a bunch of points, so these are going to be, I would think of them as data. Those are data points, right? So the picture is you've got your points here, right? And you want to find a line that minimizes the sum of the square distances from those points to that line. Yeah? You could think of this thing as a function on the Grassmannian of lines in Rn. Think of it as a function on projector space, and you are trying to optimize it. Right? You're trying to minimize it. Okay, so let's try to write down what a Grassmannian is. So we're going to try to write these things down and sort of see what kind of structure the Grassmannian has as a set. So it is already a set. I could just leave now. There's the Grassmannian, it's a set, we're done. But it's nice in mathematics when our sets have more structure than just being sets. So, for instance, if you give me a subspace inside of f to the n, how do you specify it? You give a basis for it. Yeah, okay. So if it has a dimension k, then, yeah, fair enough. I had to do the same thing to my computer earlier. So, if it has dimension k, then it has a basis v1 up through vk. So we're going to think of all these things as being rows here. So today, these things are rows. I'm going to think of them as row vectors. You could think of them as columns. It's just a choice. It's an arbitrary choice. At a certain point later in today's lecture, we're going to see a reduced echelon form, so I figured it'd be nice if they were rows instead of columns, but it really doesn't matter. In fact, on Thursday, we'll do it in terms of columns, just so you can get used to thinking of things both ways. Okay, so if you give me a basis, this means that if you look at the K by n matrices, right? K rows, so we're thinking of this thing, right? K by n matrices. So after the K by n, this gives us the Grassmannian of K-planes in n space, right? Because if you give me a K by n matrix, then you get a vector space, a vector subspace of dimension K, right? No. What's wrong with this statement? What's wrong with what I've written here? There's a couple things wrong with it. What's the first one?
You don't know that all of the rows or columns are linearly independent.
Yeah, so the first thing is that this matrix doesn't have to have rank K. Right, so the first thing I want to say is that, so this is no. So if I put a question mark here, the answer is no. What we first need is that we need rank K. So what I'm going to do is I'm going to write f to the K by n and put a little star there. And that star is going to tell me that the things are full rank. So they have rank K. Okay, this matrix, the matrices of size K by n, their rank is at most K if K is less than n, right? And so this thing, the matrices of size K by n that look like this, the rank can be at most K. The star means you're saying looking at maximal rank. So rank equals K. Okay, what else is wrong with this statement? So I'll take this thing. Now what's wrong with it? Certainly if you give me a K by n matrix of rank K, now the row span of that matrix is a subspace of dimension K. What about the arrow going the other way? If you give me a subspace of dimension K, do I get a matrix of size K by n?
No, you have to consider the column space too.
So in what sense do you need to consider the column space? Yeah, so the column space, so you know that the column space is going to be all of f to the n, all of f to the k. And because the matrix has rank k, the column space is all of f to the k. So you don't have to think about the column space. This star is already telling you that the column space is all that you need it to be. which is since the thing has rank K of the columns actually span F to the K. Now, you were saying something, and I want to hear louder.
It's because when you can choose your basis vectors via scalar multiple of other basis vectors.
Not just scalar multiples, right? So what he said is that you could choose a basis. And if you chose a basis, you could choose a different basis. So there's no natural way to go from a subspace to a particular choice of K by N matrix. In fact, how bad is the choice? So the point is I have to erase this, right? Now, what kind of arrow should I be using here? So I have a map from F. So if you give me a K by N matrix of rank K, I certainly get a subspace. Do I get all subspaces that way? All K-dimensional subspaces that way? Yes, I do. So this is surjective. It is, however, the problem not injective. And it's not injective, and how bad is the non-injectivity? That's the question that we're asking here. So the point is that it takes a matrix A, and it maps it. Pardon me while I rewrite a little bit of this. I'm going to erase that GK and just write it a little higher. I'm writing the same thing. I'm just moving it up so I can fit my mapping. This is going to be GK of F to the N. And I'll write my arrow up here. Surjection. And it's going to take this to the row span, if you like, the span of the rows of A. Okay? So this is surjective, but not injective. So in what sense is it not injective? So for example, if we take our matrix B, let's make it 1, 0, 1, 3, and 0, 1, minus 1, 1. If this maps to a vector space V, that is V is the row span, make sure this is a capital, V is the row span of this matrix, then I claim that A prime, if A prime is the matrix 2, 0, 2, 6, 1, 1, 0, 4, but this also maps to V. How do you know that this also maps to V? What's the relationship between these two matrices?
Are they related by Gaussian elimination?
Well, they are, actually. So what is this one in terms of that one? So they're rated by Gaussian elimination, so this means it's what?
First row, second row,
I mean, yes, but what do you use Gaussian elimination to do?
You multiply the first row by 2, and well, first you add the first row to the second row, replace it with some.
Oh, you're actually finding the relations between these things. What's the name of this matrix? If I gave you this matrix, what would you call this one? Say it again? I would call it the echelon form. This is the reduced echelon form of this one, right? In particular, this means, so I'm going to write something here. This is since, right? Since A prime is equal to, now you know what it's going to be times A, right? Because this is an identity matrix. So if you're going to multiply this one by something to get that one, it has to be this little matrix in here. You see that? So this is going to be 2, 0, 1, 1 times A. And because, so how do you read this equation? You read this equation as saying that the rows of A prime are linear combinations of the rows of A. Now, because this matrix is invertible, the rows of A are also linear combinations of the rows of A prime. Right? Just take the inverse matrix and put it over there. Yeah, so this says that the rows of A prime are linear combinations of the rows of A and vice versa. So they span the same row space. That's the idea here. Yeah, so the choice, going back to here, this is surjective. If you give me a k-dimensional subspace, a k-plane, then you could choose a basis. But you can also then multiply that basis on the left by any matrix of size k by k, and you'll get another basis. Is what I just said true? No, it's not. Why not?
Multiply by an invertible.
It has to be an invertible k by k matrix that I multiply by. Otherwise, I will lower the rank of the product. That's right. Okay, so what have we just learned here? So the proposition, it says that A and A prime, that those are k by n matrices of rank k, then they yield the same V. They yield the same K-plane. That's if and only if the rows of A are linear combinations of the rows of A prime and that's if and only if A prime is equal to G times A for some G in F to the K by K. Is this statement still true? I have not specified that G must be invertible. What have I specified that forces it to be invertible?
Both A and A prime are rank K.
Yes, A and A prime both have rank K. So if you can express one of them as G times another, this matrix G had better have rank K. So it's forced to have rank K. So that's if and only if. The same thing, except it's G in F K by K star, which makes sense, by the way, K by K star, because I can take K equals N, and then I'm just saying that the rank has to be K. This thing is by definition equal to GLK of F. And this is the group of invertible matrices, invertible K by K matrices. This is called the general linear group. Now remember we defined group on the very first day of lecture? We're going to use that a lot. And here's the next sort of very non-trivial usage of the word group. So the point is that you can multiply matrices that are invertible K by K matrices, you can multiply them together. There's an identity matrix that's also invertible, and every K by K matrix that has rank K has an inverse. And multiplications associated with that kind of thing, right? So this is a group. We're going to use the fact that this is a group. Okay. Yeah, so the fact that we assumed that A and A prime have rank K means that if you can get one by multiplying by a K by K matrix times the other, then the K by K matrix is automatically invertible. That's what we're saying. Okay. So corollary. That means that the K planes in F to the N, this grassmannian, is, I'm going to write some funny notations. I'm going to start off with the K by N matrices. Those are matrices with K rows and columns. And I'm going to mod out by using this slash pointing that way, G, L, K of F, like this. Okay? And I'm going to write for this is called the quotient. Oh, sorry, this should be a star. Yeah. The quotient of the rank of the full rank K by N matrices modulo the action. We defined actions in the I don't know, maybe second or third lecture. I don't remember, but I'll go over what that means in a second. Of GLK on the left. So what this means is that we have, so this action, this word action here, this means that we have GLK cross, well, GLK of F cross F to the K by N to F, to F to the K by N. All right, so if you give me an invertible matrix and a K by N matrix, then you get another K by N matrix, and this one is just the product of those two. Right, and it satisfies the various axioms of this sort of associativity and that kind of stuff. But the action is at the very least a map from pairs consisting of an invertible matrix and a k by n matrix, and it gives you a k by n matrix. That map has to satisfy some properties, but this is the action. The action is this map, the thing that takes you from a square matrix and a rectangular one to another rectangular one of the same shape. Okay. So what is this? So, F star K by N modulo GLK of F, that's equal to, it's going to be equal to, let's say, bracket A, such, so that, what is that? That's going to be a subset of invertible matrices. And that's going to be such that A is in that set to begin with. F, K, phi, N, star. So this is where bracket A is, let's say bracket A is going to be a set of matrices. And I'm going to tell you what the condition is to lie in that set. So that's where A prime is in bracket A. What does that mean? That's if and only if star and star is over right here. And so what we're doing is we're making equivalence classes again. This is something that we've done before, and I'll remind you exactly how we did that. So we're taking the quotient set. So we're saying that we have this set of k by n matrices. Those are, if you like, matrices with k rows that have, sorry, matrices with k independent rows. And we're declaring that two of these matrices are to be equivalent if they're off by multiplication on the left by something invertible, or if you like, if their row spans are the same. So bracket A is going to be the same thing as saying this is going to be GLK, so general linear group, times A. That is, you're allowed to take all invertible k by k matrices, multiply them times A. That's going to give me now a set of k by n matrices, and that's going to be called the orbit of A. So let's just do an example. Let's take n equals 2 and k equals 1, which is the only example I can sort of really draw on the board. So what's the point here? So now we're looking at matrices of size alpha, beta. Those are our matrices. Think of F as being R. So what's the picture now? What is a matrix? How do you draw one? So just stepping back for a second, right? If n is 2 and k is 1, what's the Grassmannian called? Or what is a point in the Grassmannian called?
Line through the origin.
This is just a line through the origin of the plane, right? So we're looking at these kinds of things. This sort of stuff, right? We're looking at that set of lines. Okay, so if you give me a matrix, where does a matrix sit in this picture? How do you draw, where does alpha beta, that matrix, where does it sit in this picture?
Is it just the XY coordinate?
It's just a point, that's right. It's just a point in the plane. But I need color to make it distinguishable from, all the other points in the plane. Right, so this is just going to be some point in the plane. There it is, alpha, beta. Okay? Now, what is the class of alpha, beta? What is this bracket thing here? It's the line containing, so it's almost. It is the line, except that there is no origin in this picture. Right? The line is the line minus the point in the middle, because you have to have rank 1, and 0 does not have rank 1. The matrix 0, 0 does not have rank 1. Yeah? So there is the orbit of alpha beta. Right? What is a 1 by 1 invertible matrix called? What kind of scalar? a non-zero scale. Right. Yeah, so this is these kinds of matrices up to non-zero scale. So that's how you get lines, right? That's going to be true, by the way, for arbitrary projective spaces. You're going to be looking at points that you're allowed to multiply by non-zero scalars. And that's going to be the set of lines, right? Okay, so what is the Grassmannian in this case? How do I sort of draw it? What will it look like? So I'm going to look at the set of equivalence classes. Now we're back to thinking of, so this notation is really just a highfalutin way of saying we're looking at the set of these lines, right? So if I want to draw the Grassmannian, how would I do that? Ben, you have a suggestion?
Make a circle.
I could make a circle. How much of a circle do you want me to make?
Only semicircle.
Yeah, so I want this one, right? But now I'm going to go up through here, but then when I get to here, I know, oh, I've already got that one. So I do this. Now, this makes it look like the space is a half-open semicircle, or half-closed semicircle. What is it actually? If I were to say, if I would have started up here instead, and then I went around, then I put my closed point here and my open point here. There's nothing special about this point, right? So when I go around here, I just continue and I'm back here again. So this is really a circle, right? This is a circle. It's just a circle that if you want to draw it like this, it's sort of, you have to glue that point to that one. But this is really just a circle. So the Grassmannian of lines in R2 is a circle. So this says R2 minus 0. It maps surjectively onto GL1 of R, which is, people sometimes call this RP1, real projective space of dimension 1. You see why it's called dimension 1, right? This thing is sort of a curve, so it's got dimension 1. This set is much more than just a set. Right? The circle is a nice space. It's a thing that we can put a distance on it, and it's got a topology, right? We know what it means to be an open and closed subset of this circle, and so on and so forth. So that's what we're going to make precise today. So so for this, let's compare. So that's the end of the example. So now let's compare. What's V mod W, where V and W are vector spaces? Right, so we have a notion of quotient here. We're taking the quotient of this set, rank K matrices of size K by M. We're taking the quotient modulo this action of GLK. Now, we've done a quotient before. We took the quotient of V modulo a subspace W. So how was that defined? So this is going to be the set of bracket V such that little v, it's going to be bracket v, if you like, contained in capital V, such that little v is an element of capital V. And that's where, and so you notice here I have a where A prime is in bracket A if and only if. What's the corresponding statement here? This is going to say that little v prime is in bracket V if and only if, and then what's the condition? That's right. So this is going to say little v prime is in bracket V, if and only if v prime is in, I'm going to write it as W plus little v, because that makes it look like this thing over here, right? This is all of the set, all of the group GLK acting on a single element A. This is the orbit of A. This is the group capital W acting on the single element V. This is the orbit of V, which we know is to be a translate of W. Right? You can think of it as V plus W, but here I want to think of it as W plus V. Right. So this is the coset of V. So the coset of V is really, by definition, the orbit of little v under the action of capital W on capital V. Orbit. little v under the W action. Under the action of W on capital B. Right? So this may take some time to get used to, but it's worth comparing what this quotient feels like to what this quotient feels like. And the picture that you should have in your head is really this one or some higher dimensional version of this one. Okay, it's taking R2 minus the origin, and you're declaring that each line is its own equivalence class. And we're looking at the set of those equivalence classes. Note, if we had used columns, so if instead of rows, we had used columns, then what we get is that G, K, F, and col is going to be equal to F to the n by K star, and then the modulo would be on the right. And this is the important part. It's n by K instead of K by n. So you have to multiply by the invertible matrices on the right. Yeah, it's this picture. That's all. That's the only difference.
Can you repeat the part of left and right?
Say again?
Like, this, the notation in the upper right corner is the same as this one?
This is the same as this, except that here you're multiplying on the right, and here you're multiplying on the left.
Okay.
That's the only reason I put the modulo on that side. Fair enough? Makes a difference because here things commute, right? It doesn't matter whether I went v plus w or w plus v, but here things don't commute. So I can't multiply this matrix by the little k by k one on the right. Just those matrices don't multiply. Okay, so suppose at the left k columns of our matrix A, remember this is F star k by n. F star k by n means that some, as Noah was saying, some k columns are independent. Some set of k columns is independent, right? Because if it has rank k, that means its column rank is k. So some of those k, so there is a set of k columns that's independent. Let's suppose that the left k columns are independent, as they were in this example. Yeah? So what we have is a picture that looks like this. And we've got this thing here. And that's going to be k, k. That's going to be now n minus k. Looking at this, oh, sorry, I suppose I should draw them as columns like this. Yeah? So there's our k columns. And I can call this submatrix, I can call that G. Okay? That G, the whole point is an invertible matrix of size k. Agreed? That's just what I've said. I've said the left k columns are independent, so that's just what it means. Okay, so let G be this matrix that has G1 up through Gk, and that is now an element of GLK. Okay, that means it's invertible. So now what? So now I can define A hat. So if this is our matrix A, then I can define A hat to be G inverse A, which is just going to be, what is that going to look like? It's still going to be the same shape, but now what can you tell me about the left-hand block of A? It's the identity. That's right. And then we've got stuff. Whatever that stuff happens to be, it is. This is the reduced echelon form of to a k-plane V implies that A hat also maps to the same k-plane V. This is the lesson that we've learned in the last few minutes. Multiplying on the left by an invertible matrix does not change which subspace you go to. Reduced echelon form is unique. That's what's really convenient. Reduced echelon form is unique. So this stuff tells you exactly which subspace you have. And that is in essence in bijection with a subset of the Grassmannian, right? Whatever stuff you put here tells you which subspace you get from A, but if you had a subspace that came from a matrix whose left block was invertible, then it was the subspace. Then if you tell me what this stuff is in its reduced echelon form, that tells you the subspace uniquely, right? There exists unique, right? Reduced echelon form is unique. That's convenient. So here's a little lemma. It says that if A prime maps to V, then A prime hat is equal to A hat. Why is that? That's why. This is true in this assumption. This is part of the lemma. We are assuming here that the left K columns are invertible. Otherwise, the reduced echelon form involves some columns that aren't in the first K. So what happens if you have columns that aren't in the first K? So here's another way to say this. Let's think about this one just for a second, with the same columns being invertible. So this says that A in rank K, so A in K by N matrices of rank K, such whose left columns are invertible, whose left K columns, actually not left K, I'm sorry, left K columns being the identity, actually equaling the identity. I want to say that that injects into G bed of F to the N. So this lemma is the same as that lemma. So equivalent to that lemma. And it's what I was saying before, that if you have a matrix whose left K columns literally are the identity, then the stuff that's over here determines the subspace uniquely. And that's because the reduced echelon form is unique. Now, if you give me a matrix whose left K columns are independent, then there's a unique matrix, G, that you can multiply by the inverse of to get this thing in reduced echelon form, and that's because the reduced echelon form is unique. So matrices of this form uniquely give subspaces. If you change the stuff to stuff prime, then you've changed the subspace that you're mapping to. That's what this says. If you fix the identity matrix to be here, or frankly, if you fix any matrix to be here, and then you change the stuff that's over here, then you're changing what the row span is. That means you have an injection from this set of matrices with left columns the identity into the Grassmannian K-planes. This is a really important statement. Let me tell you what we're about to do with it. This says the left K columns being the identity. That was not important. I could have made this any set of K columns. If any set of K columns is the identity, then the rest of it uniquely determines which subspace you get. And we know that every rank K, K by N matrix, has some K columns independent. So I'm going to be able to just say that, well, that means the Grassmannian is going to be covered by sort of sets that look like this. So let's go into more detail there. I'm going to explain that in a lot of detail.
So wouldn't we have that this is a bijection?
Oh, is this a bijection? This is an injection. Is it a bijection? It's a good question to start with. Ben?
I think it is.
You think this is a bijection? So you're telling me that every subspace of F to the N can be represented, is the row span of a matrix whose left K columns are independent.
Yes.
Okay, that's a good supposition, but let's try this.
Also, does that statement, one more time, mean that matrices with the same co-kernel correspond to the same hyperplane or not?
Co-kernel, so you're thinking of, so a matrix can represent a map either way. You're thinking of it as a map going from F to the N to F to the K, or from F to the K to F to the N?
Actually, from F to the N to F to the K.
You're saying it's which way, which way?
Like right multiplying or multiplying on the left.
Which way should I point the arrow? Are you thinking of row vectors or column vectors?
Column vector.
You're thinking column vectors, so we're taking F to the N to F to the K. And what about that? You want to take the co-kernel? The co-kernel should be 0 because this map is surjective. Why is that map surjective?
Because you're over-determining.
I'm not over-determining, I'm just, that's why. It has rank K, which means that the map is surjective. Yeah. Does that answer the question that you were asking, or?
Well, I was just thinking the stuff after the identity determines the constraint equations for the linear transformation, right?
I have to bend my mind to think about that for a second. Okay. Yeah, so if I put another vector over here, yes, but I can put anything over there and I can solve it uniquely because it's surjective. Sorry, I can solve it because it's surjective. I can solve it uniquely. Right?
Yeah.
We can talk more in office hours to try to clear up which point you're trying to, I'm not sure which point you're trying to make. There is a point in there to be made, but I'm not sure what point you're trying to make at the moment. Okay, so is this surjective? And what about this matrix? What rank is this matrix? Anyone?
E2.
Why is it rank 2?
Because 1, 0, and 0, 1 are linearly independent. And the rest more.
Yeah, thank you, Gary. It's because, I mean, there's still an invertible submatrix in here. It's just not the left-hand one, right? So this matrix, this is not in, and okay, let me give this map a name. Let me call this map pi. I'm going to call it pi. Is that what I want to call it? I gave it a name here. Yeah, pi sub bracket k. So here, bracket k is going to be the set 1 up through k. Okay? So it's not in the image of pi sub bracket k. Right? There is no way to span this subspace by a 2x4 matrix whose left-hand 2 columns are independent. Because no matter what you multiply on the left by, this column is going to stay 0. Fair enough? Okay, so we need more. We need more than just this. This is going to give us what turns out to be an open subset of the Grassmannian, but it's only going to be a proper open subset. There's going to be other stuff, and this is going to be some of the other stuff. So, so the rank of A equals K implies that some K columns, some set sigma of K columns is independent. So let's write, let's write F K by N sub sigma to be the set of, let's call them A hats, even though they're not actually echelon forms, in F to the K by N star, such that A hat has the identity matrix IK in the columns from sigma. Okay, so instead of the left-hand columns being independent, like this, I'm saying there's going to be some subset of columns that's independent. In this case, it's, let's say I could take these two, or I could take those two. Those will also be independent, right? but I can't take the first one and anything else. So here's going to be, so for instance, let's see now, the left K columns of A are independent. So this is going to be the set F K by N sub bracket K. Now, it's just the matrices where this block happens to be invertible. What can you tell me about the relationship between this set of matrices and this set of matrices? What's the relationship between these two?
Aren't they the same?
No, this one says that the left K columns are equal to the identity. And this one says that they're invertible. So what's the relationship between those? Right, that it's many to one. Right, see, I can take this G and multiply by the inverse of it. And that's going to give me an element over here. And if I take this guy and multiply it by any of the invertible K by K matrices, I'm going to get something of this form, right? So what I'm saying is that you know, sort of for each of these, the orbit has a unique representative here. Yeah? So inside of here, if I look at these matrices and say, all right, well, let me just look at these and multiply them all by invertible K by K matrices. Then if I multiply by the correct invertible K by K matrix, I end up with one that looks like this. And the one that I get here is unique. There's a unique one that looks like this. So for these things, there's a unique one in here that gives me the same subspace as the one that I started with. That sounds like the map to the Grassmannian, which is the point that we have this map to the Grassmannian. That's what's going on here. We're getting sort of most subspaces this way, but not all of them. Okay, so let's say what lemma double prime is. Lemma double prime says that F K by N sub sigma, and the only difference here is that this says that the left K columns, so let's see now. Right, so this says the left K columns of the identity, and this says that my fixed subset of columns is the identity. So for instance, here sigma is 2 and 3 inside of 1, 2, 3, 4, right? So this says that F sigma K by N, that also maps injectively into the Grassmannian of K-planes in F to the N. For all, and here's a funny notation that you might like, it's going to be sigma, and it's going to be in bracket N, choose K. Now, raise your hand if you've seen the notation N choose K without the brackets. Yeah, it's just a set of K element subsets of, sorry, it's the number of K element subsets of 1 through N. This is the set of K element subsets of 1 through N, right? This says you're taking the set 1 through N and you are selecting a K element subset. So instead of taking a number and selecting how many sort of numbers there are the appropriate size, you're taking the actual sets themselves. So this is going to be, I'll write this as 1 up through N, choose K. So it really is what the notation says it is, right? It's this set, choose K elements. So this is a nice notation for writing the K element subsets of a set. And that's the statement. There is a statement in here, right? The statement is that this arrow it's an injection. I want to call that pi sub sigma. So the statement is that pi sigma is injective. But it doesn't look like there's a verb in this sentence, but there is. This arrow is a verb, right? It says that the map taking the K by N matrices with identity blocks in columns from sigma, the map taking that to their row spans is an injection from this set of matrices to that set of subspaces. Just like it was over here. This arrow is easier to understand. But in some sense, it's the same thing. It's just, I'm just changing which set of columns are equal to the identity block. That's all. It's the same thing. So this is you know, like little, actually, maybe I'll do it this way. That one. That. Yeah, there was a question.
Okay, bracket entries K is a set of sets, right?
It's a set of sets, yes. It's a set of subsets. So if you like, it is a subset of the power set of 1 through n.
Wasn't there a sort of like easier way to solve this? If you just like swap the columns of ones where it isn't on the left and then multiplied by the inverse of that like submatrix?
So you could, so now what you're doing is you're multiplying by a permutation matrix on the right, and a k by k matrix, invertible k by k matrix on the left. You could do that, but it's better to keep track for the moment of which, so when you do that, you have to remember which permutation you used. So you can say that, okay, if I move these columns to the left over here and then put the zeros over there, then I have a matrix that's in this form. That's true, but now I have to remember which permutation I just did. Instead of remembering which permutation I did, let me just remember which columns were the identity block. It's equivalent in some sense. Actually, it's easier to remember the subset than to remember a permutation. Permutations are more complicated than subsets, you'll find at a certain point. Okay. So let me write this up again. F sigma k by n. That's going to map to injectively into G, the grassmannian of k planes, in F to the n. What kind of set is this? What is that? What kind of set is that? Well, first of all, it's contained inside of all of the k by n matrices, right? Forget the star for the moment. These are all k by n matrices. What kind of subset of this is this? So what kind of set is this? It's not just a set. What additional structure does it have? It's a group, that's true, or?
It's a vector space.
It's a vector space. There we go. That's a vector space. What can you tell me about this guy? Why am I not able to draw that arrow like that? What can you tell me about this guy as a subset of that one? What kind of subset is it?
Is it a subspace?
What kind of subspace?
Linear
Is it a linear subspace? Look at this picture. Tell me whether this picture is a linear subspace. Look at all matrices with identity blocks over here. Is that a linear subspace?
No.
Why not?
Add two of them, then you don't have the identity anymore.
Yeah, because 0 isn't in there, right? Because you can't have the 0 matrix doesn't have an identity block there. How could you take every one of these guys and make them into something that's got 0 there?
You just take away that identity?
Subtract off the matrix that has 1s there and 0s there. Then you get a subspace. Therefore, this is a what kind of set? Say it again. This is an affine subspace. Of dimension?
Okay.
Yeah, the throwaway stuff is the most important thing here, right? This identity is just like, okay, well, I know that's the identity. This is the information I'm interested in, even though I sort of wrote it in this kind of stuff. The stuff is the important thing here. How much stuff is there dimension-wise? It's written here already, right? No, it's not written there. It's written here.
N minus k by k.
It's k times n minus k of dimension k times n minus k. Okay, so what I'm saying now is that, so I claim that this thing, this is, first of all, this is pi sigma. So what I'm going to claim is that this thing is open. What do I mean by open? Well, that means that this thing has to have a topology on it. So I'm supposed to know what an open subset of that thing is. Aha! So now we're getting somewhere. So I want to say that here's the summary proposition. it says that the Grassmannian of k-planes in n space is covered by n choose k affine spaces, if you like, affine spaces, and let's call them f sigma k by n, injects into, by a map called pi sub sigma, into the Grassmannian of k-planes in n space. And that's then going to be the union over all subsets of size k, of 1 through n. That's choosing the columns, the independent columns, or the identity columns, if you like, of g, k, sigma, where all that gk sigma, let's say the image of pi sigma, let's call that g sub k over sigma. So this is just a summary of everything that we've just discussed. Right, because every matrix, every k by n matrix of rank k has k columns independent. So you can choose the sigma to be that sigma such that the k columns are independent, multiply that matrix by the inverse of whatever block you've got there, and then it'll be an identity block. This is the structure that's going to allow us to say what kind of set the Grassmannian actually is. It's going to be a space, it's going to have a topology, and it's going to be much more than that. So what kind of space? So raise your hand if you've seen this concept before. Not many, which is what I expected. So I expected this would probably be the first time you'd see this. So we're going to do this completely from scratch. But the point is you have enough background now to do it. So a manifold is, first of all, a topological space. So that means I know what it means for a subset to be open. This is why we did norms earlier, because I needed you to know what a topology is by the time I get here. The first time I taught this course, I didn't know I was going to teach norms. So I had to do this without knowing what an open set was. That was hard. So it's going to be a topological space X with an atlas. What's the English definition of atlas?
Map.
It's a map, but it's sort of a big compendium map, right? If you, so you're probably all too young to have had atlases in your cars or in your parents' cars. So we used to drive around with books filled with pages, and the pages were just they were maps of little areas. And the book covered the entire region, like the entire state of Maryland or something like that, but each page was just a little piece of it. This really is the right term. This is a collection of maps, and the maps are going to cover the space that you're interested in knowing about. Each page, which is going to be called, you know what, they don't call them pages for whatever reason, but you can think of them as being pages. Each page is going to cover some open subset of the space that you're interested in. And the union of those open subsets is going to be the whole space that you're interested in. So this really is like an atlas of pages that cover a map of a region. So this is going to be a set of maps, which is what you think it is. It's a set of maps. This may be why they're called maps, actually. So it's going to be U alpha, just a regular map, I call it U sub alpha, maps injectively into X by something called pi sub alpha, such that, and then we have some conditions. So first of all, X is going to be the union over all alpha of the subsets X alpha, where X alpha is the image of pi alpha. So the parallel to here should be clear. Like you should be thinking about this example. I'm going to go through this in a little bit more detail, but so this is a map from an open subset into the Grassmannian. So here the atlas is going to be indexed by the k element subsets of 1 through n. And this map from f sigma k by n into the Grassmannian is going to be one of these maps in the atlas. Okay. And for all alpha, we have that U alpha is supposed to be open in X. Oh, sorry, in F to the D. I'm sorry, I want to say this. This is supposed to be, this is the affine subspace condition. So F to the D, or some D. So let's say a manifold of dimension D. So what's D here?
It would be K, right?
So we're going to want this thing to be open inside of a vector space of dimension D. It's K times n minus K. So this is an affine space inside of a vector space of dimension K by n, but I can make it into an open subset of a vector space of dimension K times n minus K. Now, it's not canonically isomorphic, or so there's no canonical bijection with a vector space of dimension K times n minus K, but one of them is to, for instance, do this and then subtract off the identity from the block, and that gives you a vector space of dimension K times n minus K. Right? So here the D here we're looking at is this K times n minus K. That's the D that we're looking at. Okay, so all of these charts, that's what they're called. These are called charts. A set of maps, these things are called charts. I knew there was a word for it, I just couldn't think of it. Yeah, so this set F, K by N sub sigma, these have identity blocks in the columns from sigma, and that makes this set into an open subset of a K times N minus K dimensional vector space. Actually, it's in bijection with the whole vector space of dimension K times N minus K, right? It's just the bijection is that you take this set to this thing minus 1, 1, 1, 1, 1, 1, 1, 1. Okay? Okay, so we want U alpha to be open inside of a vector space. And we want that pi sub alpha, we want that to be a homeomorphism. Oh, this is the word homomorphism with an extra E, homeomorphism. And that's a topological notion. And this is going to say that U alpha maps homeomorphically to X alpha. And what that means is that this thing means that if W contained in U alpha is open, that's if and only if the image of W, so pi alpha of W contained in X alpha is open. So what it says, in short, is that U alpha, the picture that you're supposed to have here, is that you've got your space like this. So something like this. This is your space X here, and you've got some open set. This is supposed to be open inside of some vector space. And so this thing is going to map into here, and its image is going to be some open subset here, like this. Yeah, that's the picture that you've got. And I want to say that a subset in here is open if and only if this corresponding subset in here is open. That is, a blue subset here is open if and only if the blue subset here is open. Okay, the point is just mapping this open subset to an open subset over here. Okay, and I want to say that the subsets here are open if and only if their images are open over here. So if you want to know what it means for a subset of the Grassmannian to be open, what you do is you say, oh, well, I mean, if I had, for instance, a subset where I was looking at, oh, I already erased it, but where the left-hand blocks are the identity matrices, I just look at the matrices with identity blocks there and say, is that an open subset of matrices? Okay? let's see, we need one more thing. And that's going to be, the last one here, is that for all alpha and beta, I want that if I do pi alpha, so if I do pi beta inverse after I do pi alpha, that's going to map u alpha beta, I haven't told you what that is yet, to u beta alpha is, so now I have to draw some more pictures here. So that's going to be u alpha. Suppose that I have another one here. All right, let's call this u beta. Right, and that's going to map up to here, and it's going to map to some subset that looks like that. Right? So what's this, by the way, what's that blue thing here? What's this called? By name. It's the image of u alpha under the map pi alpha. This is the map pi alpha. This is the map pi beta. What's the image of pi alpha called? That's x alpha. Yeah, so that subset up there, that's x alpha. This red subset up here, that's going to be x beta. Now, what would I like to call this subset here?
X alpha beta.
I would like to call that x alpha beta. What would I also like to call that subset there?
U alpha. The image of U alpha beta.
So I want to call that x alpha beta, but I want this also to be called x beta alpha. And so what's happening here is I've got this subset here, right? That's going to be called u beta alpha. Is that visible to the people in the room? Only kind of sort of. Do you want me to use yellow instead? Let's see what happens if I use yellow. Let's call that u beta alpha. Let's call this x alpha beta. Let's call that x beta alpha. Is that more visible? Is that visible to people online? Yes. Okay, good. So this is u beta alpha. This is the subset of u alpha that goes to the yellow stuff up here. There is a corresponding set over here, which I'll call, this thing is u, I'm sorry, that's u alpha beta. This is u beta alpha. So u alpha beta is inside of u alpha. U beta alpha is inside of u beta. Okay, so what I'm trying to say is there should be a relationship between this set and that set. Yeah, so if I go from here by pi alpha, and then by the inverse of pi beta, that's what this says over here, right? I'm doing pi alpha, that's going from this subset up to there, and then I'm going pi beta inverse, it's going from this subset down to there, and this is starting from u alpha beta, and it's going to u beta alpha, right? So I've got a map that goes from this yellow stuff to that yellow stuff, and that's pi beta inverse of pi alpha. Understood what's going on here geometrically? I'm just saying I've got two charts, and I'm looking at the intersection of those two charts. On their intersection, I'm going to get a map from here to there. And I need that map. So remember, u alpha is inside of a vector space. It's an open subset of a vector space. U beta alpha, so u beta is an open subset of a vector space. So I now have a map from an open subset of a vector space, that's u alpha beta, into an open subset of a vector space, that's u beta alpha. I should like that map to have some properties. I don't want it to be an arbitrary map. What kind of map do I want it to be? What do I want to require about this map? Hints? Guesses?
Bijection.
It is a bijection already, actually. It's forced to be a bijection because these things are injective. So this is actually forced to be a bijection. So I didn't actually define u alpha beta. So u alpha beta, let's write that up here. U alpha beta is going to be pi alpha inverse. Oh, I wanted to draw that in blue. So this should say u alpha beta is pi alpha inverse of, and this is going to be x alpha beta, and that's contained in U alpha. That's open. But x alpha beta is the same thing as that's defined as x alpha intersect x beta. Fair enough? So this says it's a subset, so these are all subsets. So this is already a bijection by definition. But I want it to be more than just a bijection. I want it to be a continuous bijection. And when I require that these maps are continuous, what I get is called a topological manifold. I could want them to be more than continuous. I could ask that they be differentiable. These things are differentiable, and what I get is called a differentiable manifold. Differentiable is pretty weak condition, relatively speaking, stronger than continuous. I could ask for it to be more differentiable. I could ask for it to be C infinity or infinitely differentiable, which is called smooth. Which is also called C infinity. And then what I get, any guesses? Smooth manifold. Okay, I could require more than smooth. There's something that's better than smooth. So smooth just means it has derivatives of all orders. I could require it to agree with its Taylor series of all orders. So agree with its Taylor series. I could ask my function to agree with its Taylor series, which needn't be the case. Even if it has infinitely many derivatives, it might not equal its Taylor series. But if it does equal its Taylor series, then what I get is called an analytic function. Any guesses as to what this is called? Analytic manifold. Now, by the way, here this is R, this is R, this is R, this is R, or C. The vector space, underlying vector space can be the reals or complexes. What would have happened if I had a field that wasn't one of these things? And there's one more condition I can put. So what are the easiest continuous, differentiable, smooth analytic functions that you know of? Yeah, exponential is nice and analytic. It actually does satisfy this, but I want even easier than exponential.
Sines and cosines?
Polynomials, sines and cosines are just exponentials we saw earlier, right? Polynomials are finitely many terms, so they of course have to agree. So now we're going to say this is going to be a ratio of polynomials. Anyone know, want to guess what this thing is called? Your guess is not going to be right. It's called a rational algebraic variety. By the way, in French, the word for manifold is variété, which trips up a lot of people on the French language exam in graduate school. Now, the words variety and manifold mean the same thing. Think about it, right? They just mean like, ooh, it's got lots of something, right? Variety means you got a bunch of manifold opportunities, a variety of opportunities, same thing, right? In French, they're the same word, unfortunately. So, and I kind of, this one, so this is any field F. This is any F. This one implies this one, which implies that one, which implies that one, which implies that one. So this is a list going down in, so this is the strongest condition. This is the weakest condition. And the theorem is that G, K, F to the N is one of these. And it's a rational algebraic variety. And we'll prove this next time. We're actually going to write down the proof. It's very easy, actually. It comes down to, you're taking a matrix, and you have to multiply it by the inverse of something on the left. And the inverse, the entries are filled with rational functions of the entries.
What does it mean for that? Why is that?
Why is what open? Yes, okay, so let me be clear. This is not open inside of here. This is not open. But F sigma K by N is, it maps homeomorphically to F sigma K by N minus, and let me call it 0 sub sigma K by N, which is the matrix that has an identity block in columns from sigma and zeros elsewhere. This is a subspace. That's a vector space. And so I'm saying that this F sigma K by N really is a copy of that vector space. If you like, all I'm saying here is that this is an affine subspace. And so I'm thinking of it as an open subset of the corresponding subspace, corresponding linear subspace. So although it's an affine space, I'm thinking of it as a vector space. So I'm just saying that if you have this line, that line is not a vector subspace of R2, but it is homeomorphic to that one. Right?
So what is the notion of, what do you mean when you say it's open?
Oh, I mean, this is the whole space. So this thing maps bijectively to this thing, and the image is the whole thing. So it's open because it's the whole space.
It's not open in the R2.
It's not open in R2. It's open, this thing I'm considering as being an open subset of R1, of this copy of R1. Because it's the whole thing. That's right. Yeah. So this open subset of is meant for a more general notion. But in fact, our charts are going to have, so they're going to, the sources of our charts, these things are actually going to be, copies of vector spaces. They're not equal to vector spaces, but they are copies of vector spaces, and I can consider them for all purposes of manifolds. This space is indistinguishable from that space. So I'm going to use this space as the model for this space.